So when we first discovered the atom, we weren't actually too sure about how it looked like, and that's why we developed different models. And those models themselves could be tweaked and updated based upon evidence. And so when you do a new experiment, or you might collect new evidence or new data, you can change what you think the model should look like and what the atom should actually look like based on that new evidence. And that's exactly what happened when we had the atomic model being developed. And so first of all, before the discovery of the electron, we thought that atoms were thought to be tiny spheres that couldn't be divided. So initially you might have the atom that looks like this. There wasn't very much detail here, and we thought this was indivisible. Okay, so we didn't realize that there was anything smaller than the atom. We thought this was as small as it possibly got. And then we did some more experiments, and we actually discovered the electron. And when we discovered the electron, that actually changed how we thought the atom might look like. And instead we developed what we call the plum pudding model. Now the plum pudding model is one that comes up quite a lot in your exams, so you should be familiar with what it actually means. So the plum pudding model essentially tells us that the atom is a ball of positive charge with negative electrons embedded in it. So remember, here we discovered the electron. So after we discovered the electron, we developed this plum pudding model. And as a result of discovering the electron, we now need to implement that into our model. And so that's where we can see that actually the atom no longer looks like the first part, but instead we have this ball of positive charge. So this is all positive charge. And within the ball of positive charge, you have embedded in it these negative electrons. And so basically it's called the plum pudding model because back in the day, a plum pudding looked like this. We might have bits in a ball like this, some kind of dessert. Then we actually did the alpha particle or the alpha scattering experiment. And this was quite a key experiment because again, it actually led us to discover a few important things about the atom. And essentially what happened was you had this alpha particle emitter over here, which was emitting alpha particles. Now, those of you that don't know, and we will go into this experiment in a bit more detail later, but the alpha particle is made up of it has a positive charge. It's made up of 2 protons and 2 neutrons, but all you need to know, it has a positive charge. And so we fire this at a sheet of gold leaf like this, and the gold leaf has atoms embedded within it. And what we notice about the alpha particles is that if you put a detector on this side, then what happens is that most of the alpha particles went straight through. And actually, this is not really what we're expecting, because if the atom looked like the plum pudding model, then what we'd expect is that the alpha particles would be blocked from passing straight through because they'd hit our atoms. But instead, most of the alpha particles went straight through, and a few of them were deflected. So we had some deflected over here, some were, as we say, they were scattered. And what that tells us essentially is that most of the atoms were empty space. And the reason we can make this conclusion is because essentially most of them went straight through. So because of this arrow here, we're saying that most of the atoms are empty space because there was nothing blocking the alpha particles from passing straight through to our detector. But some of the alpha particles were deflected, and this deflection was as a result of the electrostatic charge. So this positive charge is now really important. So because we know the alpha particles have a positive charge, if they're being deflected, that means there's some electrostatic force. And electrostatic force happens when you have opposite charges or like charges. And when you have like charges, you actually get repulsion, and that's where you'd get this deflection. So here we can say actually that within the atom, there would be a small, dense, positive center. So from doing this experiment, we're actually able to develop our model with these 2 key facts. 1, that it's empty space, most of it, and 2, that you actually have a small, dense, positive center. So using this then, we now want to adapt our model of the atom. So previously we had the plum pudding model, but now we know that's probably not accurate, and we want to implement the findings that we made from our alpha scattering experiment. So now what would it look like? Essentially what we'd have is in the middle, you'd have a nucleus with a positive charge where all of the mass is concentrated. So you have the mass, and around the nucleus, you could have these electrons orbiting around. And this was kind of developed a little bit later with a guy called Niels Bohr. But essentially, the main conclusion after the alpha scattering experiment was that you have the nuclear model. And this was the introduction of the nuclear model, where you have this nucleus now. Okay, so before we just had the atom as being indivisible, then we had this plum pudding, and now we actually have this concept where we have a middle of the atom, this nucleus. Okay, so that's where the nuclear model came in. And so essentially the nuclear model was then adapted by Niels Bohr to say that actually these electrons, they orbit this nucleus at fixed distances. Okay, so that's where Bohr came in. So here we've got fixed distances. And we don't need to know too much about the details of how we came to that conclusion, but essentially the same pattern was happened here again. So you did experiments. There's a Niels Bohr character. He came along, he made some suggestions. Then he did some experiments. They agreed with his theoretical calculations, and therefore this model was then updated to say that these electrons orbit the atom or the nucleus fixed distances or specific distances. Later then we took this positive nucleus and we did some more experimentation, and later experiments said that actually this ball of positive charge, which we know as our nucleus, can be separated into several smaller parts. And so instead of having this big ball we'd have the nucleus made up of smaller positive particles or subatomic particles, and this is where the proton comes in, and so these were called protons, okay? And so again, more experimentation means that we developed the model further to say that these are protons. Then James Chadwick came along. He did some more experimentation, as you might have figured out by now, and he discovered the existence of neutrons. And as a result, then once again the model that we had was updated to include these new features. And so essentially now what we have in our modern nuclear model is a model of the atom that looks like this, where you still have your positive nucleus in the middle, but it's actually made up of two different types of particles. So the first type of particles are neutrons, and they have no charge. They're neutron charge. The second type of particle are protons, and both of these particles together make up your nucleus. And you can see you've got some particles with positive charge, some particles with no charge. So overall, the nucleus will have a positive charge. And so we'll draw that like that. So you do have your nucleus still, and that's why it's still known as the nuclear model. And around that, you have electrons orbiting at specific distances, very much as we mentioned before. And actually, it might look something like this, where you have some electrons orbiting at a certain distance and other electrons further out. Okay, and you'll see this model a lot more, and we'll talk about it in more detail. But essentially, what it is important to know is how this model was developed. And the key thing we need to identify, and hopefully you've seen from us talking through it, is actually when we do more experiments and we gather more data and more evidence, then we want to update our model to actually fit those observations in. Okay, so let's do a few questions before we end off the video. And a few questions just to get you thinking. Feel free to answer these questions out loud or write them down on a bit of paper. So question 1, describe the plum pudding model. So hopefully everyone got that the plum pudding model is described as a ball of positive charge with the negative electrons embedded within it. Describe the nuclear model. Well, the nuclear model actually has a dense positive nucleus in the middle made up of protons and neutrons, and orbiting around it at specific distances are the electrons. What did Chadwick discover? Well, Chadwick was the one that discovered the neutron. What triggered the development of the plum pudding model? The plum pudding model was actually developed when the electron was discovered. So if you remember, I mentioned at the beginning, once the electron was discovered, we realized that our atomic model wasn't really suitable, and that's why the plum pudding model came in. And what did Bohr change about the nuclear model? Well, Bohr actually added the fact that the electrons orbit at specific distances. Now, one thing we didn't cover in this quiz is actually the concept of the alpha scattering experiment, which is quite important. So I'm going to add it in here. So if you can just describe the alpha scattering experiment for me now. So the alpha scattering experiment, what happened was you had alpha particles being emitted from an alpha particle emitter, a detector on the other side, and a thin sheet of gold leaf in the middle. What we noticed was two observations. The first one was that most of the alpha particles passed straight through and was detected on the other side. Some of the alpha particles were deflected. And so the two conclusions were made. The first one was that because most of the alpha particles passed straight through, that means that most of the atom was empty space. And the second is that because some of the alpha particles were deflected, that means that in the middle of the atom, there has to be a small dense positive center where most of the mass is concentrated. And those were the two conclusions that we came to as a result of the alpha particle scattering experiment, and that actually helped develop the nuclear model that we know today. Okay, so hopefully you got those correct, and I'll see you in the next one.